Physics 112. All right, this is the first of a couple of videos on chapter 28. We're also doing chapter 29 this week. And we'll have a quiz on this the following Monday. This stuff's not too bad. Chapter 28, 29, chapter 30 gets a little more complicated again, but this is all, I think, fairly straightforward. So this is just about magnetic fields, chapter 28, and the force that a magnetic field can exert on charged particles. So capital B is the symbol that we use for the magnetic field. It's a vector, so it has that vector sign on top of it, and it's called the magnetic field. It's a capital B, not capital M, because capital M is pretty much used for masses and things like that. It has a unit which is officially a Tesla, which is a capital T. The Tesla is a Newton times a second divided by a Coulomb and a meter. So it's a pretty complicated little unit there. You could write it more basically in terms of kilograms and things like that instead if you wanted to, but typically this is how we think of Teslas, and we'll see why in a minute. So magnetic fields can be produced in kind of two different ways. So some elementary particles, specifically like an electron, have an intrinsic magnetic field. This is like a basic characteristic about the electron. Just like it has mass and it has charge, it has a magnetic property, which we call, and it produces the magnetic field. So it has an intrinsic little magnetic field. We're all full of electrons. Most of objects, the magnetic fields basically are chaotic or not aligned inside your object, and so they all cancel out. But permanent magnets are objects where all the electrons have been aligned so that their magnetic fields add together, and then you end up with this magnetized object. And again, that's only for permanent magnets. A regular object has lots of electrons, but the magnetic fields would all be canceled out. And so you don't notice any net magnetic field. You can also produce a magnetic field with an electrical current. And this is called an electromagnet. And so when you have current flowing, you have the magnet. When you turn the current off, your magnet goes away. This is a really safe way to have a really strong magnetic field, because you can just have it on when you need it, and then you can turn it off when you don't. Magnetic fields are not necessarily intrinsically toxic or dangerous, but they can interfere with the magnetic fields that need to exist inside the human body or something like that, and that can cause damage in that sense. It's not really like radiation like gamma rays or something like that, but it can interfere in any case. By the way, a Tesla would be a tremendous amount of magnetic field. Most of the time we have things which are much, much weaker than a Tesla for a magnetic field strength, although things can be produced that are Tesla in strength. In chapter 28, we're going to focus on the force that magnetic fields can exert on charged particles. So charged particles are not only responsive to each other through the electrostatic force, but they also respond to the magnetic field. And in fact, the basic force, the force of nature is actually called the electromagnetic force. And it manifests itself as either an electric field or a magnetic field, depending upon the frame of reference that you're in, which is far more than you probably want to need to know in Physics 112. But it is a natural force, and we see it as both electric fields and magnetic fields. But it always cares about charged particles. So magnetic fields and electric fields are fields that act upon something that has a charge. It doesn't the force does not care about the fact that something has mass like gravity does. It cares about the fact that the object has some sort of charge. So again, magnetic field is a vector. So that means it has a magnitude and a direction. And like we had for the electric field, we can draw magnetic field lines. We can draw magnetic field lines. So here's just an example of some magnetic field lines. So here I've drawn magnetic field lines, and they're all going to the right and they're sort of uniform. So this is a uniform magnetic field that's directed towards the right, or maybe we could even write this as the positive x direction or I hat direction. Here I have another uniform magnetic field that's moving up and to the left. And again, I'm drawing the magnetic field lines. Here I've actually got a bar magnet. So a bar magnet is just like, you've probably seen a bar magnet. It's just usually it's made out of iron, because iron is easy to get the electrons to line up in. And a bar magnet has a north pole and a south pole. And the magnetic field lines always point away from the North Pole and towards the South Pole. And in many ways, this magnetic field lines look very similar to the electric field lines around a dipole, right? When we did in lab, when we had a positive charge and a negative charge, we had electric field lines that went like this, and they kind of curled around on the outside. They went like that. And so again, this looks very similar to sort of an electric dipole, but it's a magnetic field. So they're not electric field lines, they're magnetic field lines. But again, they point from, so magnetic field lines point from the North Pole to the South Pole in this manner when they're outside of our bar magnet. We're also going to have lots of times where we're going to have magnetic fields pointing in and out of the paper. And it won't just be the magnetic field. Sometimes we'll have maybe current going into the paper, or maybe velocity going into the paper. And so when we draw a vector and we're saying that vector is going into our paper or into our board, we draw these crosses. So the cross says this is going into the board. Let's see if the book has got something similar to this. I've got it coming out of the board. If we're having coming out of the board, we draw little dots. And so here in this figure of the textbook, here they're drawing the magnetic field coming out of the board. So they're not doing the circles around it, they're just doing the dots. This is supposed to be imagining some arrow, and this is supposed to be like the tip at the front of the arrow, and the cross signs are supposed to be the back of the arrow. That's supposed to be like the feathers on the back of the arrow. Let's see if they can find a picture where they're showing it. So here they're showing a magnetic field going in. So a cross means in, a dot means out. So it doesn't have to just be magnetic field. If you see a cross, that means into the paper is the direction. If you just see a dot, that means out of your paper as your direction. So in case you see something like that, that's what that means. So it turns out that when you have a charged particle and it's moving, so it has some non-zero velocity. If it's moving, so it has to be moving, it has to have some non-zero velocity, and it's in a region where there's a magnetic field, there'll be a magnetic force. This is also called the Lorentz force. In case anybody ever asked you, this is the Lorentz force. And the amount of the vector force turns out to be the charge, and that's not an absolute value around that charge, it's the actual charge. And then it's multiplied by the cross product of the velocity with the magnetic field. So this is a vector cross product in here, and the vector cross product we did back in chapter 3 in Physics 111. A vector cross product means that you end up with a vector at the end, which is what we need because we have a force, and that's definitely a vector. The there were sort of two ways we could do it. One was straight up doing things with our I hat, j hat, j hat, k hat, where we have, components x, y, and z components for both of our vectors. In this case, our vectors are v and b, not a and b. Or we could also use this relationship where we said, well, the magnitude of this vector product is going to be the magnitude of the first product vector, the magnitude of the second vector, and then the sine of the angle between them. And then we'd get the direction of that force from the right-hand rule. In our situation, looking at this second way, if we say that basically our magnitude of our force is actually going to be, and these should have absolute values around them. Let me rewrite this. So just to be clear, we're saying the magnitude of the charge, the magnitude of the velocity, the magnitude of the magnetic field, and then the sine of the angle between them. That's how we could get the magnitude of the force. And then the right-hand rule, this is the right-hand rule specifically for velocity versus crossed with the magnetic field. Remember that when we do the right-hand rule, what you basically do is you put your fingers, so you have to use your right hand first of all, you put your fingers in the A vector, the first vector's direction, and then you curl your fingers or sweep them over to the B vector's direction. And then your thumb will point in the, let's say that this was equal to C, was our final vector. If we say C vector is A cross B, then would point in the C director direction. So here they're showing us a situation where the velocity would be this way. So they first put their fingers in that direction, and then they move their fingers towards the B direction. So they move it over so it's lined up with B, and their thumb is sticking up like this. Right? Their thumb is sticking up like that. That tells them that the force on a positive particle is that direction. Now, negative particles have to go the exact opposite way, right? A positive particle and a negative particle do exactly the opposite thing. So in this situation, F sub B would be down on a negative particle, and here F sub B would be up on a positive particle. So I'm going to call this, by the way, right-hand rule number 1 for this semester, because we're going to end up with 2 more. So we're going to have right-hand rule number 2 and right-hand rule number 3, which your book doesn't necessarily do, but I do, just to help keep this straight. This right-hand rule number 1 is the big right-hand rule. But the other 2 can be very helpful in terms of some other stuff we're going to do. So I want to just do a couple of examples here where we just sort of say, okay, here's a charged particle and here's a V and here's a magnetic field. What's the force? What's the direction? What's the magnitude? So let's just, I've got 4 charges here, Q1, Q2, Q3, Q4. The blue ones have a positive charge. The red ones have a negative charge. They're all existing in a region with a 10 Tesla magnetic field, God bless them, and they all have a magnitude of their velocity of 10 meters per second. So the magnitudes are supposed to be the magnitude of the charge, the magnitude of the velocity, the magnitude of the magnetic field, and then the sine of the angle between the velocity and the magnetic field. Well, they all have these angles that exist between the V and the magnetic field are all 90 degrees. It's just the angle between them. It doesn't have to be it's not a positive or negative. It doesn't go from one to the other. It's just the angle between them. And they all have the same magnetic field, magnitude, 10 Tesla. They all have the same speed, 10 meters per second. And they all have the same Q magnitude as well. And so they are all going to have the same magnitude of the force. It's going to be 10 times 10 to the negative 10 coulombs, 10 meters per second, 10 Teslas, and the sine of 90, which is 1. So when I do all this, I get 10, let's say 5, 4, 3. This should be 1.0 times 10 to the negative 3, and that's a Newton. Let me double check it just to make sure. 10 to the negative 6 times 10 times 10. Yep. So they all have the same magnitude of force. But the directions are going to differ here. So to get the directions, I'm going to go to each of these. Unfortunately, y'all can't see my hands, but we're going to try to follow what they did up above. So for this first one, for Q1, I'm going to put my fingers of my right hand in the direction of this velocity. So I'm going to put my fingers in this direction along the velocity. And then I'm going to, when I do that, my thumb is pointing down. Is your thumb pointing down? You should be doing this along these. So your thumb should be pointing down into it, or for y'all, if you're watching this on a screen, my thumb is pointing into the screen. And so then if I try to turn my fingers so that they go along the magnetic field line, right? So now I'm trying to get my fingers, I'm going to curl my fingers in the direction of the magnetic field line. My thumb stays down. And this is a positive particle. And so here, what I'm getting is that the magnetic force on Q1 here, I'll put this in black. The magnetic force on Q1 is into the screen. It's into the screen. And so I could draw it as a little circle with a cross on it. It's into the screen from the right-hand rule. For Q2, now I'm going to do the same thing. So my fingers will go along the V. They'll curl. So I turn them so that they're now moving along here. My thumb is still in, but the Q2 is a negative charge. And so that means that I flip my hand over, and so F sub B is out of the screen for Q2 because it's a negative charge. With Q3, now my fingers are going to point down, away, down along the V, and then I try to turn them so that they go along the magnetic field. For me to do that, my thumb is pointing out, and this is a positive charge, so F sub B is out of the screen on my positive charge here. For Q4, my fingers point along the velocity, and then they curl and move just like I just did for Q3, but this is a negative charge. And so that means that my thumb then needs to point into the board or into the screen because it's a negative charge. So for a negative charge, you're going to flip the direction that you get from what I call right-hand rule number 1. Right-hand rule number 1 will tell you the direction for a positive charge. If it's a negative charge, you have to say it's going to go the exact opposite direction. Let's do a couple more. So here, now I have, let's pretend like the amounts are still the same thing here, 10 meters per second, 10 Teslas, and 10 microcoulombs. But now I have, again, a positive charge and a negative charge, but they are at an angle, more of an angle, the velocity with respect to the magnetic field. So once again, the magnitude of the magnetic field is going to be the 10 times 10 to the negative 6 coulombs, 10 meters per second, 10 Teslas. But now my angle between my magnetic field and my velocity, if the smaller angle is 70, then the phi is 110 degrees, right? And so I say 110 times that, sine of 110. So this is my same answer from before, but now I'm multiplying it times the sine of 110. Just a second here. Sorry, I had my calculator in radians, which won't work. So I get 9.40 times 10 to the negative 4 newtons. So it's slightly smaller, this force. And again, it's because I'm not getting the vector cross product. The biggest number you're going to get is when your two vectors are orthogonal to each other, perpendicular to each other. And so here, when we have our velocity perpendicular to our magnetic field, we get the largest force. But when we have a slight, you're off from that, we're off from that by 20 degrees, then that means we get a slightly smaller force. If you have a velocity which is along the magnetic field, then you get no force at all. Right. Direction-wise here, again, so let's think about our right-hand rule. So for my first vector here, my first charge, I'm going to put my fingers along, with my right hand, I'm going to put my fingers along that velocity line, and then in order to have my fingers sweep towards the magnetic field line, my thumb has to be pointing into the paper for that to happen, for my hand to be able to go that way. And so that, for me, that means that my thumb is pointing into the board. This is a positive charge, and so the magnetic field force is into the screen. Similarly, if I do velocity crossed with magnetic field, my thumb is pointing in, but this is a negative charge. And so the magnetic force is out. Okay, let's look at another example. Here, again, we're going to go with everything still the same. Number-wise, V is still 10 meters per second. Magnetic field is still 10 Teslas, and our charges have a magnitude of 10 microcoulombs. And so once again, our magnetic field magnitude here, our magnetic field is into the paper and our velocities are to the left. That angle between to the left along here and the magnetic field is still 90 degrees. So our phis here are 90 degrees. Hopefully y'all can see that. And so this ends up being the same magnitude as we had in our first example, where our magnetic field is perpendicular to our velocity. But here we can actually see the force. So let's try this. So if I put my fingers along this velocity line for my positive charge, and then I basically turn my hand so that my fingers go into the screen with the magnetic field, then what I see is that the force, my thumb points down like this. right? My thumb points down for the magnetic field force on this positive charge particle. For the negative charge, again, I put my fingers of my right hand along the velocity. I then push my fingers into the screen, and my thumb is pointing down, but this is a negative charge particle. So I have to flip this and say the magnetic field, or the magnetic force points upwards. Yeah, hopefully you're seeing that. One more with these things. So again, here now I have the magnetic field pointing out of the paper with the same situation. But again, our angle here is still 90 degrees between our velocities and our magnetic field. The magnetic field is coming out of the paper. Our velocities are to the left. That's a 90-degree angle. And so this also has a magnitude of 1.0 times 10 to the negative 3 newtons. Here, if I put my fingers for my positive particle along the velocity, and now I want my fingers to go out of the screen, my thumb is going to be pointing up. Similarly for Q2, I have a negative charge. I have my fingers along the velocity. They curl out. My thumb is pointing up, but this is a negative charge particle, and so F sub B is down. I am going to try to do some of this tomorrow in class, or one in-person class this week, just to try and help out with that a little bit more. All right. So what happens if I put a charged particle in a region where there's both a magnetic field and an electric field? I have both of them there, and they're both going to exert a force on that charge. A big thing that does this, and our chemistry majors maybe have seen this, or I'll show exactly where we're going to use this. It's called a velocity selector. It's used inside a mass spectrometer, or before objects enter the actual spectrometer part of it. So here I've got a region where I have electric field lines which are running vertically here on my paper or on my screen. And then I have magnetic field which is coming out of my screen. So the magnetic field is coming out of the paper. Electric field is moving up. And so say I have a positively charged particle here. So looking at this positively charged particle, a positively charged particle would feel an electric force that goes along the electric field lines, right? It's going to want to go up like this. And from the magnetic field, I put my fingers in the direction of the velocity, and then I curl my fingers in the direction of the magnetic field, which is out of the board, and my thumb is pointing down. So that tells me that there's a magnetic force pointing downward. So free body diagram wise, if I said, okay, here's my Q, this Q feels an electric force which is up. It feels a magnetic force which is down. I can write this as an F net, essentially Y equation, where I pretend this is positive Y, where I say, okay, I have F sub E up, I have FB down. A velocity selector, essentially what you want is only certain things, only objects that have certain velocities to actually make them across. So velocity selector, only particles with some specific velocity make it across. So you want it to basically move like this. So you want these forces, you want an acceleration to be 0. You don't want it to move up in y. You don't want it to go down in y. Let's see if I actually have, here's a velocity selector. So here's a charge, and see here it's actually falling down. So I don't want that. So I'm gonna change my electric field a little bit and see if that helps. Actually, it doesn't have a magnetic field, which is part of our problem. So here it's actually showing me the strength of my magnetic field is actually going up on this one, and the electric field is going down. That magnetic field is too strong. It's causing it to move too much. Let's actually increase our electric field and see if we can balance them out. So we want to try and balance these so that this particle goes straight across. Oh, it's so close. It's like the world's most boring video game. Oh, there we go. So there we've got a balance between our electric force and our magnetic force, and that object makes it through the velocity selector. So a velocity selector, you'd want this to be equal to 0 so that the acceleration was 0. So if I do that, then I basically am saying that the magnitude of my electric force has to equal the magnitude of my magnetic force. This is Q times the electric field. Whereas this is Q, and these are just magnitudes here in both Q and E. So this is Q, V, B. Here the magnetic field is a line perpendicular to our electric, to our velocity. We have Q on both sides. And so the V that makes it through, the velocity that makes it through, is the magnitude of the electric field over the magnitude of the magnetic field. This is the velocity that can pass through on our thing. And it's hard to see the values over here. Let's pump this all up and we'll... Too strong. These values are too small to see in this simulation. I have a better simulation to watch in a little bit. Another thing I wanted to look at is what happens to, say, this positive charge particle inside this region with a magnetic field. Let's look at this a little more depth. Back to the path of, I have a positive charge particle, but in a region with a magnetic field. So we did this before, basically, well, I'm going to make that, it's very distracting. Let's see if I can get this to stop doing that. All right, so here, again, I'm going to have my velocity to the left, so I'm going to do my cross product. Let's just look at the directions here. So my fingers on my right hand are directed towards the right, to the left, and then I'm going to curl my fingers into the screen, and so my thumb is pointing down. So there's going to be a force, F sub B, which is going to basically try to pull it down. That plus the original velocity is going to cause this particle to basically go on a path like that. And so there'll be a time when the particle is now at this place. When it's there, it's going to have a velocity which is this way. So now if I do my cross product here, now my fingers are going to be pointing down, and then my fingers have to curl into the screen, and now my thumb points, oops, let's blow this up. My thumb is going to point like this. Now my magnetic force is going that way. That's going to cause my particle to curve like this. So now my particle will be down here, my charge, and it has a velocity at this location, which is, again, still tangential to its motion. If I do my cross product here, again, my fingers go in the direction of the velocity, and then they go into the board or into the screen, and I get that the force goes like this. That's going to cause my particle to curve and come over here. And so now it's at this location. It has a velocity this direction. If I do the cross product here, my fingers in the direction of the velocity, they move, turn and go into the board. My thumb is pointing towards the left. And that causes my particle to come back up to here. The motion of a particle, of a charged particle in a magnetic field. Path of a particle in a magnetic field is a circular path. And in fact, this is uniform circular motion, where F net is being caused by the force that's here, that's acting on it, is the magnetic force. And the motion that we see, if we have uniform circular motion means that the acceleration is a sub c, which a sub c is v squared over r. And so this is m v squared over r, where the direction of this is radial. So again, if we say, okay, well, the magnitude of the magnetic force is qvb, and the angle here between our velocity and our magnetic field is 90 again. So this has to equal mv squared over r. I can move these around and I can basically say, well, the radius of the circle that it's making here, the radius of this circular path that it's following, is going to be is mv squared over qvb, and one of those velocities can cancel out. So the radius of the circular path depends upon the velocity that the object had. It depends upon the mass that the object has. It depends on the charge that the object has and the magnetic field strength of the region that it's in. You can also rewrite this as the mass that the object has. Right? If I solve this the other way around, if I say QBR over V, the mass that the object has depends upon the charge, its magnetic field, the radius of the path, and the V. Now, it's not really that way. Mass does not really work that way. Actually, let me just forget I said that, because we'll talk about that here in the mass spectrometer. So combining a velocity selector with this idea that you can get these circular paths depending upon the masses of the particle, this is a mass spectrometer. So let me look at, where did I put that? No, not my Discord channel. Here we go. So a mass spectrometer, how are we doing on time? Oh, I'm way over time. Never mind.